You are made of carbon. That is not a poetic statement. It is a chemical fact. The proteins folding inside your cells right now, the DNA carrying instructions that have been copied without interruption for 3.8 billion years, the amino acids doing the actual work of keeping you conscious long enough to hear this sentence. All of it is built on a backbone of carbon atoms. Carbon is the fourth most abundant element in the universe. It is in every living thing ever discovered. It is so fundamental to biology that when scientists search for life on other planets, they do not look for life. They look for carbon. And carbon should not exist. That is not an exaggeration. It is not a simplification for dramatic effect. The pathway from helium to carbon, the specific nuclear reaction that has to occur inside a dying star to produce every carbon atom in your body, should not work. It requires a coincidence so precise, so unlikely, so dependent on a single number falling in exactly the right place, that when a physicist first calculated what that number had to be, the experimentalists at Caltech thought he was out of his mind. He turned out to be right. The number was exactly where he said it would be. And the fact that it is exactly where it is, and not a fraction of a percent higher or lower, is the reason you exist. I want to tell you how I ended up spending weeks on this topic, because the entry point matters. I was reading about stellar nucleosynthesis, which is the process by which stars build heavier elements from lighter ones, and I hit a detail that stopped me. The detail was this: the universe, for the first few 100 million years after the Big Bang, contained no carbon. None. The periodic table did not exist. There was hydrogen, helium, and a trace of lithium. And that was the entire chemical vocabulary of the cosmos. Everything else had to be manufactured inside stars that had not yet formed from matter that had not yet cooled enough to clump. And the specific reaction that bridges the gap between helium and carbon, the one that makes everything else possible, depends on a nuclear energy level that was unknown to science until a man predicted it should exist from the simple observation that he was alive. That fact lodged in my brain and would not leave. I have spent a genuinely unreasonable amount of time on this topic, weeks, and what I found is not a single strange coincidence. It is a pattern that stretches across every domain of physics, from nuclear energy levels to the expansion rate of the universe, from the mass of the electron to the number of spatial dimensions. And every attempt physics has made to explain this pattern has either failed catastrophically or produced an answer more disturbing than the question. Here is the problem. After the Big Bang, the universe was made almost entirely of hydrogen and helium, with trace amounts of lithium. That is it. 3 elements. Everything else, every atom of carbon, oxygen, nitrogen, iron, calcium, phosphorus, everything that makes up planets and oceans and bones and brains had to be manufactured later. Inside stars, stars are nuclear furnaces. They smash light nuclei together to build heavier ones. Hydrogen fuses into helium. That part works beautifully. The sun has been running on hydrogen fusion for 4.5 billion years and has enough fuel to keep going for another 5 billion. The process converts roughly 0.7% of the mass of the fuel into energy via E equals mc squared. A small percentage, but when you are working with the mass of an entire star, the numbers add up fast. The sun converts about 4 million tons of matter into pure energy every second. It has been doing this since before the first multicellular life appeared on Earth, and it will keep doing it long after you and everyone you know are gone. But hydrogen to helium is the easy part. The hard part is everything after. The wall is at atomic mass 5 and atomic mass 8. No stable nucleus exists at either of these masses. Helium is mass 4. If you smash 2 helium nuclei together, you get beryllium-8, mass 8. And beryllium-8 is one of the most unstable nuclei in nature. It exists for approximately 8.19 times 10 to the negative 17th seconds. That is about 82 attoseconds. To put that in some kind of perspective, 82 attoseconds is to 1 second what 1 second is to roughly 400 million years. Beryllium-8 does not exist in any meaningful sense. It appears and it is gone. So the path from helium to carbon should be blocked. 2 helium nuclei make beryllium-8, which vanishes before anything can happen to it. To get to carbon, you would need a 3rd helium nucleus to collide with the beryllium-8 during that impossibly brief window. The probability of this 3-body collision happening at a rate sufficient to explain the observed abundance of carbon in the universe is, under normal circumstances, essentially 0. Edwin Salpeter at Cornell worked this out in 1951. He calculated that inside red giant stars, at temperatures above 100 million Kelvin, a tiny equilibrium concentration of beryllium-8 could accumulate roughly 1 beryllium-8 nucleus for every 100 million helium nuclei. A 3rd helium could then be captured, but the rate was far too slow. And worse, even the small amount of carbon that did form would immediately be consumed by further reactions that turned it into oxygen. You would end up with a universe rich in oxygen and almost completely devoid of carbon. But here we are, made of carbon. Lots of it. In early 1953, a man named Fred Hoyle arrived at Caltech for a sabbatical. Hoyle was born on June 24, 1915, in Gilstead, a small village near Bingley in the West, Riding of Yorkshire. His father survived the Battle of the Somme. His mother, who had trained at the Royal Academy of Music and accompanied silent films at the local cinema, taught him the 12 times table before he started school. He had the kind of blunt, stubborn, argumentative Yorkshire personality that made him simultaneously one of the most brilliant and most infuriating scientists of the 20th century. He attended Bingley Grammar School and won a place at Emmanuel College, Cambridge, to read mathematics. His doctoral supervisor at Cambridge was Paul Dirac, who we will meet again later in this story. Hoyle later described the arrangement as the student who did not want a supervisor paired with the professor who did not want a student. During the war, he worked on radar for the Admiralty alongside Herman Bondi and Thomas Gold. And in 1948, the three of them proposed the steady-state theory of the universe, the only serious rival to what Hoyle himself, during a BBC radio broadcast on March 28, 1949, dismissively called the Big Bang. The name stuck. Hoyle denied he meant it as mockery. Nobody believed him. He occupied an office in the Kellogg Radiation Laboratory at Caltech and ran a weekly seminar he titled Experimental Cosmology, which was characteristically provocative since Hoyle had never been an experimentalist in his life. The problem that consumed Hoyle at Caltech was the carbon problem. He knew the triple alpha process, as the 3-helium to carbon reaction was called, could not produce enough carbon at the rate Salpeter had calculated. But carbon exists. Hoyle existed. Therefore, the reaction must proceed much faster than Salpeter thought, by a factor of roughly 10 million. And the only mechanism in nuclear physics that could produce such an enhancement was a resonance, a specific excited energy state of the carbon-12 nucleus that would act like a doorway, amplifying the reaction rate by letting the 3 helium nuclei combine through a preferred energy channel. Hoyle calculated what the energy of this state had to be. The combined rest mass energy of beryllium-8 plus helium-4 sits 7.3367 million electron volts above the carbon-12 ground state. Add thermal kinetic energy from the stellar core, roughly 0.32 million electron volts, and the resonance had to sit near 7.65 to 7.68 million electron volts. Hoyle predicted it would be at approximately 7.68. He then walked into the office of William Fowler, the director of the Kellogg Radiation Laboratory at Caltech, and told him this nucleus state had to exist. Fowler thought he was insane. Previous experiments had looked for excited states of carbon in this range and found nothing. But Hoyle would not leave. He was, by all accounts, relentless. Fowler eventually relented and assigned Ward Whaling, an experimentalist who had joined Kellogg in 1949 after his PhD at Rice, to look for it. Whaling's team, which included the Australian visitor Noel Dunbar, William Wenzel and Ralph Pixley, used a Van de Graaff accelerator that they had to roll down a hallway on tennis balls to reposition. They bombarded nitrogen-14 with deuterons and looked for the decay products. Hoyle had returned to Cambridge by the time the results came in. The resonance was found at 7.68 plus or minus 0.03 million electron volts. The modern accepted value is 7.6549. Hoyle was right, not approximately right to within the experimental uncertainty of the measurement. Fowler later said that from that moment, they took Hoyle very seriously indeed. But here is where it stops being a cool story and becomes something genuinely unsettling. The Hoyle state, as this resonance is now called, does not just have to exist. It has to exist at almost exactly the energy where it was found. In 2000, Oberhammer, Cisoto, and Schlattel published a paper in Science showing that outside a 0.5% window in the strong nuclear force strength, either carbon or oxygen production in stars drops by factors of 30 to 1,000. Shift the strong force by 0.5% in one direction, and stars produce almost no carbon. Shift it 0.5% in the other direction, and stars produce carbon but virtually no oxygen. And you need both. The chemistry of life requires both. The window in which the strong force produces both carbon and oxygen in roughly comparable abundances is not just narrow, it is a razor. And it gets worse. Even if the Hoyle state produces enough carbon, there is a second reaction that should immediately destroy it. Carbon-12 can capture another helium-4 to produce oxygen-16. If this reaction proceeded at a resonance-enhanced rate, all the carbon would be burned to oxygen. But oxygen-16 happens to have an excited state at 7.12 million electron volts, which sits approximately 45,000 electron volts below the threshold energy for the carbon plus helium reaction. It just barely misses being a resonance. If that oxygen state were a tiny bit higher in energy, just above the threshold instead of just below, it would resonate with the incoming helium and destroy every carbon atom produced. Two independent nuclear energy levels in two different elements, both of which have to be positioned within narrow tolerances of their actual values for you to exist. Carbon for the backbone of organic molecules, oxygen for water and respiration. Both required, both independently balanced on a razor. And there is a further layer. Once carbon exists in the universe, it becomes a catalyst. In stars more massive than about 1.3 solar masses, the dominant energy production mechanism is not direct hydrogen fusion, but the CNO cycle, independently proposed by Carl Friedrich von Weizsäcker in 1937 and Hans Bethe in 1939. Bethe received the 1967 Nobel Prize partly for this work. In the CNO cycle, carbon, nitrogen, and oxygen serve as catalysts in a 6-step reaction loop that converts 4 protons into one helium-4 nucleus, releasing about 26.73 million electron volts per cycle. The energy production rate scales as roughly the 16th power of temperature. The CNO cycle is why massive stars burn so much faster and hotter than our sun, and why they explode as supernova, scattering heavy elements into the interstellar medium where they eventually form planets and people. Without the Hoyle state, there is no carbon. Without carbon, there is no CNO cycle. Without the CNO cycle, there are no supernovae of the type that distribute heavy elements. Without those supernovae, there is no solar system. The entire chain hangs on a single nuclear resonance. Let me walk you through the actual mechanics of this reaction, step by step, because the details matter. Step 1. 2 helium-4 nuclei collide and form beryllium-8. This reaction is endothermic. It costs about 91.78 thousand electron volts, and the product, beryllium-8, is so unstable that its resonance width is roughly 6 electron volts, which corresponds to that half-life of about 82 attoseconds. Inside a red giant core at 100 million Kelvin, a tiny equilibrium concentration of beryllium-8 builds up. Roughly 1 in 100 million helium nuclei exists as beryllium-8 at any given instant. Step 2. A third helium-4 nucleus collides with the beryllium-8 during its brief existence. This is where the Hoyle state becomes critical. The resonance at 7.6549 million electron volts acts as a doorway, an energy level that the combined system can fall into, vastly amplifying the rate of this reaction. Without the resonance, the probability of this capture is vanishingly small. With it, the rate increases by a factor of roughly 10 million to 100 million. That is the difference between a universe with negligible carbon and a universe where carbon is the 4th most abundant element. Step 3. The excited carbon-12 nucleus, now in the Hoyle state, has to de-excite to the ground state. And here is another piece of the fine-tuning that almost nobody mentions. The Hoyle state is a 0+ state. The carbon-12 ground state is also 0+. A direct gamma-ray transition between 2 0+ states is absolutely forbidden by angular momentum conservation. It cannot happen. So how does the carbon survive? It de-excites through a rare process called internal pair creation, emitting an electron-positron pair instead of a photon. This happens in only about 1 out of every 2,421 transitions. The other 99.96% of the time, the excited carbon simply falls back apart into 3 helium nuclei. The universe produces carbon through a forbidden transition that works 1 time in 2400. The net energy released per carbon-12 nucleus produced is 7.275 million electron volts. Every carbon atom in your body was manufactured through this exact sequence of improbable events. Inside a star that no longer exists, at temperatures you cannot imagine, through a resonance that was predicted by a man who reasoned backward from his own existence. In 2011, Evgeny Appelbaum and colleagues achieved something remarkable. They calculated the Hoyle state from first principles using lattice chiral effective field theory, running simulations on Germany's Eugene supercomputer. This was the first ab initio calculation of the Hoyle state, meaning they did not put the resonance in by hand. They derived it from the fundamental interactions between quarks and gluons, and it appeared at the right energy. In their 2013 follow-up paper, they found that carbon-oxygen-based life can withstand variations of up to about 2.5% in the fine structure constant and about 0.15% in light quark masses before the Hoyle state shifts enough to be fatal. 0.15%. That is the margin. That is how close to the edge we are. I personally think this is the most underrated part of the entire fine-tuning story. People talk about the cosmological constant. People talk about the multiverse. Almost nobody talks about the fact that your existence depends on two nuclear energy levels in two different atoms, both happening to sit exactly where they need to sit, independently, for no reason that physics can explain. Hoyle saw what this meant. He was an atheist. He did not want to see what he saw. But the numbers were the numbers. And in 1981, in a paper published in the Caltech alumni magazine Engineering and Science, he wrote something that would follow him for the rest of his life. He wrote that a common sense interpretation of the facts suggests that a superintellect has monkeyed with physics, as well as chemistry and biology, and that there are no blind forces worth speaking about in nature. He wrote that the numbers one calculates from the facts seem so overwhelming as to put this conclusion almost beyond question. He used the phrase supercalculating intellect. We are going to come back to what he actually meant by that, because it is not what you think, and it is worse. But first, there is something you need to understand about the carbon resonance. It is not alone. You might be thinking that this is one coincidence. A strange one, sure. Maybe even a deeply strange one. But one, a single number that happens to fall in the right place. And we are here because it did. And that is interesting, but not necessarily meaningful. That was roughly what most physicists thought for decades after Hoyle's prediction. A curiosity, a lucky break for carbon-based life. Then people started looking at the other constants, and what they found was not one coincidence. It was a pattern so consistent, so repeated across every domain of physics, that by the time you reach the end of the list, the word coincidence stops meaning anything. Start with the strong nuclear force, the force that holds protons and neutrons together inside an atomic nucleus. Its coupling constant at the relevant energy scale is approximately 0.1179. It is the least precisely known of the standard model forces, but we know it well enough to calculate what happens if you change it. If you increase the strong force by roughly 2%, something catastrophic happens. Two protons can suddenly bind directly to each other, forming a particle called a diproton, helium-2. Right now, helium-2 is unbound by about 400 to 500,000 electron volts. It does not exist as a stable particle. It flickers into existence during proton-proton collisions and immediately flies apart. The strong force is almost, but not quite, strong enough to hold two protons together. But a 2% increase closes that gap. And if diprotons are stable, then during the Big Bang, virtually all hydrogen would have fused into helium-2 before the first 3 minutes were over. The universe would contain no hydrogen, no water, no organic chemistry, No stars that burn for billions of years on slow hydrogen fusion. The universe would be a featureless soup of helium, inert, incapable of supporting any chemistry at all. Barrow and Tipler put this explicitly in their 1986 book, The Anthropic Cosmological Principle. All the hydrogen in the universe would be burned during the early stages of the Big Bang, and no hydrogen compounds or long-lived stable stars would exist today. That is what a 2% shift in one number does. Go the other direction. Decrease the strong force by roughly 10 to 15%, and the deuterium falls apart. Deuterium, one proton bound to one neutron, is the essential stepping stone in Big Bang nucleosynthesis. Without stable deuterium, the reaction chain that builds helium from hydrogen collapses entirely. You get a universe of pure hydrogen. No helium, no path to heavier elements, no stars as we know them. So the strong force sits inside a window, roughly 2% on the high side, 10 to 15% on the low side. That sounds like a reasonable margin until you realize that there is no known reason it had to land in this window at all. The strong coupling constant is a free parameter of the standard model. It is not derived from anything deeper. It is measured, not predicted. Now the fine structure constant, alpha, approximately 1/137, the most precisely measured number in all of physics, known to 81 parts per trillion, thanks to a 2020 measurement by Leo Morel and colleagues using rubidium atom recoil at the Kassler-Brossel laboratory in Paris. This constant governs the strength of electromagnetic interactions, the force that holds electrons in orbit around nuclei, that drives all of chemistry, that determines how light interacts with matter. Luke Barnes showed in his 2012 review that if you plot a 2D parameter space with alpha on one axis and the strong coupling constant on the other, the region that permits both stable complex chemistry and stellar energy production is a thin sliver. Oberhammer and colleagues found that outside a 4% window in the electromagnetic force strength, stellar production of carbon or oxygen drops by factors of 30 to 1,000. Ekstrom and colleagues went further. They found that a change of 1 part in 10,000 in alpha would prevent stars from synthesizing both carbon and oxygen. 1 part in 10,000. The gravitational constant is, remarkably, the least precisely known of all the fundamental constants. Its current best value is 6.67430 times 10 to the negative 11th in SI units, known to only about 5 significant figures. Compare that to the fine structure constant at 12 significant figures. Gravity is everywhere. It governs the large-scale structure of the entire universe, and we cannot measure its strength as well as we can measure almost anything else in physics. There is a stubborn spread of about 550 parts per million among the 13+ most recent measurements, which use completely different experimental techniques and still cannot agree. This is either a systematic problem with measuring gravity, which is embarrassing, or a clue that gravity is stranger than we think, which is unsettling. Barnes calculated in his 2012 review that the region of parameter space permitting stable stars when you simultaneously vary the gravitational and electromagnetic coupling constants occupies just 10 to the negative 38th of the available range. That is the fraction of possibility space that permits a universe recognizable as our own. The rest is sterile. The proton to electron mass ratio, 1836.15267. The neutron proton mass difference, 1.293 million electron volts. If the proton were heavier than the neutron instead of lighter, free protons would decay. Every hydrogen atom in the universe would be unstable. Craig Hogan showed in 2000 that the basic structures of the universe depend on just 5 of the 20 standard model parameters, and changes of even a few percent in quark masses, we are talking about fractions of a million electron volts, would radically alter stellar nucleosynthesis. Martin Rees, the UK Astronomer Royal and former president of the Royal Society, crystallized this in 1999 with his book, Just 6 Numbers. He identified 6 dimensionless constants that together determine the character of the universe. N, the ratio of electromagnetic to gravitational force between 2 protons, approximately 10 to the 36th. If it were much smaller, only tiny short-lived stars would exist, burning out before biological evolution could occur. Epsilon, 0.007, the fraction of mass converted to energy when hydrogen fuses to helium. At 0.006, protons cannot bind to neutrons and only hydrogen exists. At 0.008 or higher, no hydrogen remains. Omega, the cosmic density parameter, approximately 1. In the early universe, omega had to be tuned to within 10 to the negative 15th of unity at 1 second after the Big Bang. 1 part in a million billion. Lambda, the cosmological constant, contribution, approximately 0.7 in units of critical density, corresponding to 10 to the negative 122nd in Planck units, the most finely tuned number in all of nature. Q, the amplitude of primordial density fluctuations, approximately 10 to the negative 5th, an order of magnitude lower, and gas never condenses into galaxies, an order of magnitude higher, and matter collapses directly into black holes instead of stars. And D, the number of spatial dimensions. 3. Max Tegmark at MIT showed in 1997 that with more than 3 spatial dimensions, no stable atoms or planetary orbits can exist, because the gravitational force law becomes inverse cube or steeper. With fewer than 3, there is insufficient complexity for anything resembling structure. 6 numbers, each independently constrained, each sitting in its viable range for reasons that physics cannot explain from first principles. The probability of all 6 simultaneously landing in their life-permitting ranges, if you treat them as independent random draws from their mathematically possible ranges, is not small. It is a number so close to 0 that writing it down requires more zeros than atoms in the observable universe. And there is a deeper strangeness underneath all of this that goes back to one of the founders of quantum mechanics. In 1937, Paul Dirac published a short paper in Nature called The Cosmological Constants, in which he pointed out something that still has no explanation. Certain dimensionless ratios of fundamental constants produce enormous numbers that cluster suspiciously around powers of 10 to the 40th. The ratio of the electromagnetic force to the gravitational force between a proton and an electron is about 10 to the 39th. The age of the universe expressed in atomic time units is about 10 to the 40th. The ratio of the observable universe's radius to the classical electron radius is about 10 to the 40th, and the square of that number, 10 to the 80th, is approximately the number of baryons in the observable universe. Dirac could not accept this as coincidence. He argued that these large number coincidences reflected a deep connection between microphysics and cosmology that we had not yet discovered. Since some of these ratios involve the age of the universe, which changes with time, the coincidence should hold only at the present epoch, unless one of the constants is actually changing. Dirac made the radical proposal that the gravitational constant g must decrease with time, specifically that g scales as 1 over the age of the universe. In 1961, Robert Dicke provided the Anthropic resolution. The coincidences hold, Dicke showed, because they are mathematically equivalent to requiring that the universe be old enough for heavy elements to have been synthesized in stars, but young enough that stars are still burning. These are precisely the conditions under which carbon-based observers can exist. The large number coincidences are not evidence of exotic physics. They are evidence of selection. You can only ask about the numbers during the epoch when the numbers have the values that permit you to ask. Dicke's resolution was elegant, but it only pushes the question back one level. Why does a universe exist that has an epoch during which these coincidences hold? Why does a universe exist in which the constants even permit the formation of stars that burn long enough for biology to arise? The selection effect explains why we see the values we see, given that we exist. It does not explain why a universe that permits existence was available in the first place. Now, you may have heard that fine-tuning is a religious argument. It is not. I want to be very clear about this because it matters. The term anthropic principle was coined in 1973 by Brandon Carter, an Australian astrophysicist working at the Paris Modon Observatory at a symposium in Krakow, Poland, held to celebrate the 500th anniversary of the birth of Copernicus. Carter was born on May 26, 1942, near Sydney. He studied under Dennis Sayama at Cambridge, where he shared an office with Stephen Hawking. He later moved to France to join CNRS, and his other contributions to physics include the Carter-Penrose diagrams for black hole spacetimes, the Carter constant for orbits around rotating black holes, and co-developing the no-hair theorem with Israel and Hawking. He was not a crank. He was not a theologian. He was not making a theological claim. He was making a physics observation. He was pointing out that the Copernican principle, the idea that humans do not occupy a special position in the universe, had been extended too far. His formulation was careful. Our location in the universe is necessarily privileged to the extent of being compatible with our existence as observers. That is a selection effect. It is the same logic you would use if you found yourself surprised that you live on a planet with breathable air and then realized that you could not have found yourself on a planet without it. The data is the data. The numbers are measured. What you do with them is philosophy. But the numbers themselves are not a matter of opinion. So the pattern is confirmed across nuclear physics, particle physics, cosmology, and mathematics. Every fundamental constant sits inside a narrow window that permits complex structure, and the windows are independent. The carbon resonance has nothing to do with the cosmological constant. The strong force has nothing to do with the number of spatial dimensions. These are constraints from completely different sectors of physics, and they all point in the same direction. Therefore, someone must have an explanation. Surely physics, with its particle accelerators and its space telescopes and its 10,000-person collaborations, can explain why the constants are what they are. But the first attempt to explain even one of these numbers produced the worst prediction in the history of science. There is a number in physics that should embarrass everyone in the field. It has been sitting in the literature since 1967. It has been verified and re-verified by every generation of physicists since then, and nobody can fix it. The number is the cosmological constant, and the story of what happened when physics tried to calculate it is, I think, the most damning indictment of our understanding of fundamental reality that exists. The cosmological constant describes the energy density of empty space. The vacuum is not empty. Quantum field theory tells you that even in a perfect vacuum, with no particles, no radiation, no anything, there are fluctuations. Virtual particle-antiparticle pairs flickering in and out of existence. These fluctuations carry energy, and energy in general relativity curves space-time. So the vacuum has a gravitational effect. The question is, how much? In 1967, the Soviet physicist Yakov Zeldovich sat down and calculated the vacuum energy density from first principles using quantum field theory. What he got was a number so large that if it were correct, the universe would have either collapsed back on itself or blown apart before a single atom had time to form. In 1989, Steven Weinberg published the definitive review of this problem in Reviews of Modern Physics and put a precise number on the discrepancy. Quantum field theory, using the Planck energy as the natural cutoff, predicts a vacuum energy density of roughly 2 × 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ measured from the actual expansion rate of the universe, is roughly 2.5 times 10 to the negative 47th giga-electron volts to the fourth. The ratio is 10 to the 120th. I want you to sit with that for a second. Physics made a prediction. The prediction was wrong by a factor of 10 to the 120th. That is not being wrong by a factor of 2 or 10 or a million. That is a 1 followed by 120 zeros. Even Wolfgang Pauli, back in the 1920s, ran a rough version of this calculation and found that at the predicted energy density, the universe could not even reach to the moon. He apparently regarded this as so absurd that he set the problem aside and moved on. The field has been setting this problem aside and moving on for the better part of a century. It is called the vacuum catastrophe, and it is routinely described as the worst prediction in the history of physics. I have been obsessed with this number for longer than I want to admit, because the more you look at it, the worse it gets. The standard response from physicists is that some unknown symmetry must cancel most of the vacuum energy, bringing it down to the tiny value we observe. But no one has found this symmetry. Supersymmetry was the best candidate, and I would have predicted superpartner particles at energies the Large Hadron Collider should have found. It did not find them. The vacuum catastrophe remains, 58 years after Zeldovich first calculated it, completely unexplained. And then Steven Weinberg did something remarkable. Weinberg was born on May 3rd, 1933, in New York City. He grew up in the Bronx, the son of a court stenographer. He attended the Bronx High School of Science, the same school that produced Sheldon Glashow, with whom he would later share the Nobel Prize. He studied at Cornell, where he was a classmate of both Glashow and the future physicist Gerald Feinberg. He did postdoctoral work at the Niels Bohr Institute in Copenhagen and at Princeton. He won the 1979 Nobel Prize for electroweak unification, sharing it with Glashow and Abdus Salam. He was by wide consensus one of the greatest theoretical physicists of the 20th century, and his colleagues at the University of Texas at Austin considered him the greatest living physicist. He was also an outspoken atheist, perhaps the most philosophically engaged atheist in the physics community. His most famous line from his 1977 book, The First 3 Minutes, was that the more the universe seems comprehensible, the more it also seems pointless. He later clarified this remark in a 2009 interview, saying that he did not think science could decide there is no point, but it could certainly testify that it has failed to find one. He was not a man inclined toward mysticism, fine-tuning arguments, or anything that smelled remotely of design. In 1987, 2 years before his comprehensive review of the cosmological constant problem, Weinberg published a short paper in Physical Review Letters titled Anthropic Bound on the Cosmological Constant. His argument was elegant and disturbing. He said, suppose the cosmological constant is not fixed by some symmetry. Suppose it varies. Suppose different regions of a vast cosmological ensemble, different parts of a multiverse, have different values. Then what constrains the value we observe? The answer is that we can only exist in a region where the cosmological constant is small enough for gravity to pull matter together into galaxies. If it is too large and positive, expansion overwhelms gravity and nothing clumps. If it is too large and negative, the universe recollapses before stars form. Weinberg calculated the upper bound. The vacuum energy density must be no more than roughly 100 to 200 times the present cosmic matter density. This was, at the time, an almost meaningless prediction. Every physicist assumed the cosmological constant was exactly zero. Weinberg was predicting it was non-zero and positive. He was essentially alone in this. In 1992, he refined the bound. In 1995, Alexander Vilenkin at Tufts sharpened it further to approximately 10 times the matter density, about 3 times the value that would eventually be measured. Then, 1998 happened. 2 independent teams, the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley, and the High-Z Supernova Search Team, led by Brian Schmidt, with Adam Rice as first author, used Type Ia supernovae as standard candles to measure the expansion history of the universe. Both teams found the same thing. Distant supernovae were fainter than expected. The expansion of the universe was accelerating. Something was pushing the cosmos apart. The implied dark energy density was omega lambda approximately 0.7, corresponding to roughly 2.3 times the present matter density. That value was almost exactly where Weinberg said it would be. Science magazine named it the breakthrough of the year. Perlmutter, Schmidt, and Rees shared the 2011 Nobel Prize in Physics. The discovery transformed cosmology overnight. But here is the part that gets buried in the textbooks. Weinberg's 1987 paper had predicted this, not in some vague hand-waving way. He had calculated a specific bound from a specific framework using a specific assumption, the assumption that the cosmological constant varies and that our value is determined by the requirement that observers exist, and the observed value fell inside his bound. The only prediction of the cosmological constant that actually worked was the one that assumed the universe was built for us to be in it. I want to emphasize something here because it is easy to miss in the technical details. Before 1998, the scientific consensus was that the cosmological constant was exactly zero. There were theoretical reasons for this, mostly the hope that some unknown symmetry would force the vacuum energy to vanish. Weinberg ignored the consensus. He said, what if there is no symmetry? What if the value just is what it is? And then he asked a question nobody else was asking. What does life require? That question, that specific framing gave him the right answer a decade before the experimentalists confirmed it. You can draw whatever philosophical conclusions from this that you want, but the empirical fact is that anthropic reasoning outperformed every other approach to the cosmological constant by a wide margin. Think about what happened here. Physics tried to calculate the cosmological constant from first principles and got a number wrong by 120 orders of magnitude. An atheist physicist then said, "Forget calculating it, just assume it varies and ask, what values permit life?" He got a bound. The actual value fell inside that bound. The only prediction that worked was the one that assumed the universe was tuned for the existence of observers. Weinberg himself called this a disappointment. He would have preferred to derive all constants from first principles. He compared the situation to Kepler trying to explain planetary orbital radii using the 5 Platonic solids. Kepler was sure the orbits reflected deep mathematical truth. They turned out to be historical accidents, products of a messy gravitational history. Weinberg suggested the cosmological constant might be the same, an accident that varies across a multiverse, with our value selected by the requirement that galaxies must form. But he was honest about the implications. This kind of reasoning only makes sense, he said, if and only if there is a very large number of big bangs with different values of the cosmological constant in each one. Now here is a part of this story that borders on poetic, and I mean that in the darkest possible way. Weinberg spent his career trying to make the universe comprehensible from first principles. He unified electromagnetic and weak forces. He helped build the Standard Model. He believed physics should explain, not shrug. And his single most successful prediction, the one that was vindicated by Nobel Prize-winning observations, was the prediction he made by giving up on explanation altogether and simply asking what life requires. He died on July 23, 2021, in Austin, Texas, at the age of 88. The man who most wanted the universe to be explicable became the author of the argument that it might not be. I find that genuinely tragic. But there is a version of the anthropic argument that goes further than Weinberg was ever willing to go. One that does not just explain why the constants permit observers, one that requires observers for reality itself to exist. We are not there yet, but we are heading there. And the road goes through the multiverse, which is where the entire project starts to collapse. Because the obvious next question, the one that every smart person asks when they hear about Weinberg's prediction, is this: if the anthropic reasoning works, if the cosmological constant's value is explained by the requirement that observers must exist to see it, then where are all the other universes where the constant took different values? There must be other universes. Where are they? Can we detect them? Can we ever detect them? And the answer physics has offered to that question is extraordinary in its ambition and, I would argue, devastating in its implications for what we think science actually is. So here is the escape hatch that physics has built for itself. It is called the multiverse. The idea is seductively simple. If there are a vast number of universes, each with different values for the fundamental constants, then we naturally find ourselves in one that permits our existence. The fine-tuning is not a mystery. It is a selection effect. We observe a universe tuned for life for the same reason a fish observes an ocean. It could not observe anything else. The theoretical machinery behind this comes from string theory. In the late 1990s and early 2000s, physicists realized that string theory does not predict a single, unique vacuum state. It predicts a landscape. The number of distinct possible vacuum configurations, each corresponding to a different set of physical laws and constants, is commonly estimated at 10 to the 500th power. That number is so large, it is essentially infinite for any practical purpose. There are roughly 10 to the 80th atoms in the observable universe. 10 to the 500th is 10 to the 80th multiplied by itself more than 6 times. The landscape dwarfs the physical universe by a margin that language cannot capture. The foundational paper was published by Raphael Bousseau and Joseph Polchinski in 2000. They showed that with enough four-form fluxes on the compact dimensions of string theory, the allowed values of the cosmological constant form what they called a discretium, a grid of possible values so finely spaced that observationally tiny values, like the one we actually observe, are included somewhere in the grid. The KKLT mechanism proposed by Kachru, Kalosh, Linde, and Trivedi in 2003 provided a method for stabilizing string vacua with a positive cosmological constant. And Leonard Susskind, the Felix Bloch professor at Stanford, pulled the whole picture together and gave it a name. In a 2003 paper, he coined the term Anthropic landscape of string theory. In his 2005 book, The Cosmic Landscape, he called it a landscape of possibilities populated by a megaverse of actualities. The population mechanism is eternal inflation. André Linde at Stanford showed in 1986 that chaotic inflation is generically eternal. Once inflation starts in any region, quantum fluctuations ensure it never stops everywhere. Different regions stop inflating at different times, nucleating into bubble universes that cool and expand. Each bubble lands in a different vacuum state. Each gets a different set of constants. Alexander Vilenkin at Tufts independently reached similar conclusions. The multiverse in this picture is not a hypothesis. It is a consequence. You start with string theory and inflation, both of which are frameworks that many physicists take seriously for independent reasons. And you get a vast ensemble of universes with varied constants as an output. And it works. Sort of. It explains the cosmological constant, the way Weinberg described. It explains fine-tuning, the way an anthropic selection effect should. But it has a problem that may be fatal. And the physicists who first identified this problem are not fringe figures. They are the people who built the theoretical framework in the first place. Paul Steinhardt is the Albert Einstein Professor in Science at Princeton. He was one of the original architects of inflationary cosmology in the early 1980s, and he has become its most vocal critic. He has called the multiverse the death for the theory because it loses all predictive value. He has called it a multi-mess. In 2017, he co-authored a Scientific American article titled Pop Goes the Universe with Anna Ijas and Abraham Loeb, arguing that inflationary cosmology, as we currently understand it, cannot be evaluated using the scientific method. The article triggered a furious response. 33 physicists signed a letter defending inflation, including Alan Guth, André Linde, Stephen Hawking, Sean Carroll, and Susskind himself. The signatories essentially argued that inflation has made successful predictions and that the multiverse, while not directly observable, is a legitimate theoretical consequence of well-motivated physics. But the critics were not persuaded. George Ellis, Emeritus Professor of Applied Mathematics at the University of Cape Town and one of the most respected cosmologists alive, wrote in Scientific American in 2011 that all the parallel universes lie outside our horizon and remain beyond our capacity to see, now or ever, no matter how technology evolves. In 2014, Ellis and Joe Silk published an editorial in Nature titled "Scientific Method: Defend the Integrity of Physics," in which they warned that arguments for the existence of untestable theories represent a fundamental departure from centuries of empirical science. They invoked Karl Popper's criterion of falsifiability. If a theory cannot, even in principle, be shown to be wrong, it is not a scientific theory. It is something else. Peter Woit, a mathematician at Columbia University, put the circularity even more sharply in his book, Not Even Wrong. The argument, as he characterized it, runs like this: the multiverse cannot be tested, but we should believe in it because it is a consequence of string theory. String theory cannot be tested because of the multiverse. Each props up the other. Neither touches the ground. I want to be fair here. There are serious, careful physicists who believe the multiverse is the correct explanation and that the falsifiability objection is too narrow a standard for evaluating theoretical frameworks. Sean Carroll at Johns Hopkins has argued that science should be about the best explanation, not just about falsification, and that the multiverse, combined with inflation and string theory, constitutes the best explanation we currently have. Max Tegmark at MIT has proposed a 4-level multiverse hierarchy in which all mathematical structures have physical existence. These are not unintelligent positions. The people holding them are brilliant, but the fact remains: no experiment has detected a parallel universe. No observation requires one. The multiverse is a theoretical consequence of two unconfirmed frameworks, string theory and eternal inflation, and it has been elevated to the status of explanation without passing through the checkpoint of evidence. You can call it the best explanation available. You cannot call it a tested one. And in a field that spent 4 centuries building its credibility on prediction and confirmation, that is a problem that should keep you up at night. And there is a deeper issue that most discussions of the multiverse gloss over, and I think it is worth pausing on. Even if the multiverse is real, it does not actually explain the fine-tuning. It explains why we observe fine-tuned constants, which is a different thing. The multiverse says there are many universes, most are dead, and we happen to be in a live one. Fine. But why does the mathematical structure of reality permit a live one at all? Why does the landscape have any viable points? Why is the space of possible physics not entirely sterile? The multiverse pushes the fine-tuning question back one level, from why these constants to why this landscape. And at that level, the question is just as unanswered as before. Susskind acknowledges this. He has written that the landscape is a framework for understanding, not a final theory, and that a deeper explanation of why string theory has the structure it does may eventually be found. But it has not been found, and until it is, the multiverse is not an explanation. It is a deferral. It kept Lee Smolin up at night. Smolin was born on June 6, 1955, in New York City. He is a founding member of the Perimeter Institute for Theoretical Physics in Waterloo, Ontario, and he has been one of the most persistent critics of both string theory and the anthropic landscape. But unlike Ellis and Steinhardt, Smolin did not just criticize. He proposed an alternative. And his alternative is, in my opinion, one of the most creative ideas in the history of theoretical physics, even though it might be wrong. He called it Cosmological Natural Selection. He published the original paper in 1992 in Classical and Quantum Gravity. The mechanism is explicitly, unapologetically Darwinian. When a star collapses to form a black hole, Smolin proposed, the singularity does not simply terminate in a dead end. Instead, quantum gravity effects at extreme densities produce a bounce, and that bounce spawns a new expanding universe inside the black hole, a baby universe. The new universe inherits the fundamental constants of its parent, but with small random variations, mutations in effect. He elaborated the idea in his 1997 book, The Life of the Cosmos, which is, if you are interested in this topic, one of the most thought-provoking books written about fundamental physics in the last 30 years, even though it is almost never assigned in physics courses. I wonder why. Think about what this means. Universes that produce lots of black holes have lots of offspring. Universes that produce few black holes have few offspring. Over many generations, the population of universes shifts toward those configurations that maximize black hole production. It is natural selection. It is differential reproduction. It is fitness landscapes. It is mutation and inheritance. Except the organisms are not bacteria or birds. They are entire universes. And here is the key insight that makes cosmological natural selection genuinely interesting rather than merely speculative. The conditions that maximize black hole production, massive stars, supernovae, efficient nucleosynthesis, turn out to overlap substantially with the conditions that produce life. Both require long-lived stars. Both require complex chemistry. Both require a universe that lasts long enough for structures to form. Stars need to be heavy enough to collapse, but not so heavy that they blow apart completely without leaving remnants. The nuclear physics has to permit iron cores to accumulate. The gravitational constant has to allow sufficient compression. And all of these conditions, it turns out, are closely related to the conditions that permit carbon chemistry, liquid water, and the kind of stable environments in which biology can unfold over billions of years. The fine-tuning for life would be, in this picture, a side effect of fine-tuning for black holes, achieved not by design, but by Darwinian selection across generations of universes. I actually find this idea deeply compelling on an aesthetic level, even though I am not sure the physics supports it. There is something satisfying about the thought that the universe might have evolved, that the constants might be the result of a selection process rather than a coincidence or a decree. It feels more honest than the multiverse, which just waves its hand and says everything exists somewhere. It feels more grounded than Wheeler's framework, which asks you to accept backward causation through cosmic time. Smolin's idea gives the constants a history. It gives them a reason. The reason might be wrong, but at least it is a reason. The brilliance of the proposal is that it makes testable predictions. The most specific prediction is that our universe should be near optimally tuned for black hole production. No small change in any fundamental constant should increase the number of black holes our universe produces. This is, in principle, a falsifiable claim. If you could show that tweaking a constant by 1% would dramatically increase black hole production, cosmological natural selection would be in trouble. Smolin originally predicted that the maximum neutron star mass should not exceed approximately 1.6 solar masses. The reasoning was that a lower maximum mass means more stellar collapses end in black holes rather than stable neutron stars, which would be the configuration selected for by cosmological natural selection. In October 2010, Demarest and colleagues published a measurement in Nature of the millisecond pulsar PSR J1614-2230, finding its mass to be 1.97 plus or minus 0.04 solar masses. The original 1.6 prediction was clearly falsified. Smolin revised his bound upward to approximately 2 solar masses, which sits right at the boundary of the observation. Critics, including Susskind, argued that the theory also requires information transfer through black hole singularities, which the holographic principle and black hole complementarity seem to prohibit. Roger Penrose called the proposal extremely speculative, but Smolin's deeper argument was not about whether cosmological natural selection is correct in detail. It was about the nature of scientific explanation. He argued that his theory, even if wrong, is better than the anthropic landscape because it makes specific predictions that can be tested and potentially falsified. The landscape, by contrast, can accommodate any observation, which means it explains nothing. A theory that predicts everything predicts nothing. I spent a long time thinking about Smolin's framework, and here is where I come down on it. The idea is beautiful. The mechanism is elegant. It has the rare virtue in contemporary theoretical physics of actually sticking its neck out with specific claims about the world. And it is quite possibly wrong. The bounce mechanism at black hole singularities is speculative. The assumption that constants vary by small amounts across bounces is unmotivated by any detailed quantum gravity calculation. The testable predictions have either been falsified or sit at uncomfortable margins. Cosmological natural selection is the kind of idea that deserves more attention than it gets, but it is not the answer. Not yet. Maybe not ever. So where does this leave us? The pattern is real. Dozens of independent physical constants sit inside narrow, life-permitting windows. The standard calculation of the most basic constant fails by 120 orders of magnitude. The anthropic prediction works, but requires a multiverse that cannot be tested. The only alternative with testable predictions is marginal at best. Physics does not have an explanation for the fine-tuning of the universe. It has a collection of proposals, none of which meet the standard that physics itself established for what counts as an explanation. Let me be direct about what this means, because I think it deserves directness. We are not talking about a frontier problem that will probably be solved in the next decade. We are not talking about a gap in our knowledge that a cleverer theorist or a better particle accelerator will close. We are talking about the most basic question you can ask about the universe. Why are the laws of physics what they are? And after a century of effort by the smartest people who have ever lived, the answer is that we do not know. The multiverse says the question is the wrong one to ask. Cosmological natural selection says the answer is Darwinian. A hypothetical theory of everything would derive the constants from pure mathematics. None of these exist in a confirmed, tested form. The question remains open. And that should disturb you because the pattern is not ambiguous. It is not a matter of interpretation. It is a set of numbers, measured to extraordinary precision, that all point to the same conclusion. The universe appears to have been arranged for the existence of observers. And that brings us to the framework that physicists are most reluctant to discuss, because it does not just explain why the constants are tuned for life. It says the universe cannot exist without life. And the man who proposed it was not a mystic. He was not a philosopher. He was not a theologian. He was John Archibald Wheeler, and there is a reasonable argument that he was the most important American physicist of the 20th century who did not win a Nobel Prize. Wheeler was born on July 9, 1911, in Jacksonville, Florida, to parents who were both librarians. He earned his PhD at Johns Hopkins by the age of 21. He studied under Niels Bohr in Copenhagen. He co-authored the Bohr-Wheeler paper that first explained nuclear fission in 1939. He worked on the Manhattan Project. He joined the Princeton faculty, where he spent nearly 4 decades. He coined the term black hole in 1967 during a lecture at the Goddard Institute for Space Studies in New York. The story goes that he was struggling with the cumbersome phrase gravitationally completely collapsed object and asked the audience for something better. Someone suggested black hole. Wheeler used it. The name stuck. He also coined wormhole and quantum foam. He mentored Richard Feynman, Hugh Everett III, who invented the many worlds interpretation of quantum mechanics, and Kip Thorne, who would go on to win the Nobel Prize for gravitational wave detection. He also supervised more PhD students than almost any other physicist of his generation, many of whom went on to shape entire subfields. Wheeler was the kind of physicist who made other physicists feel inadequate, not because of his intelligence, which was extraordinary, but because of the breadth of his vision. He thought about physics the way most people do not think about anything. His favorite saying was that if you have not found something strange during the day, it has not been much of a day. Another one, which I think about constantly. Someday surely we will see the principle underlying existence as so simple, so beautiful, so compelling, that we will all say to each other, how could we all have been so stupid for so long? He died on April 13th, 2008, of pneumonia at the age of 96. He was working on physics until the end. What Wheeler proposed, beginning with his 1977 essay Genesis and Observership, and crystallized in his 1983 paper Law Without Law, published in the volume Quantum Theory and Measurement that he co-edited with Wojciech Zurek, was something he called the Participatory Anthropic Principle. It is a phrase that sounds academic until you understand what it actually claims. Then it sounds like the most disturbing idea in the history of physics. Start with the double-slit experiment. A particle, say a photon, is fired at a barrier with 2 slits. If no one measures which slit the photon goes through, it exhibits an interference pattern on the far side, as if it went through both slits simultaneously as a wave. If someone does measure which slit it goes through, the interference pattern vanishes. It behaves as a particle. The act of observation changes the outcome. This much is standard quantum mechanics, disturbing but well established. Wheeler took it further. In 1978, he proposed what he called the delayed choice experiment. The setup is the same double-slit arrangement, but the choice of what to measure, wave behavior or particle behavior, is made after the photon has already passed through the slits. The photon has already decided whether to go through one slit or both, and yet the measurement made after the fact determines which behavior is observed. I want you to really sit with that, because people hear about this experiment and nod along without registering what it means. A photon passes through a barrier. It either went through one slit or both. After it has already passed, you choose what question to ask, and your choice made after the fact determines what the photon did, not what you learn about what it did. What it did. The past is not fixed until a question is asked about it. This was confirmed experimentally. Vincent Jacques and colleagues published the definitive result in Science in 2007 using single photons in a Mach-Zehnder interferometer with a quantum random number generator controlling the measurement choice, ensuring that the decision was truly made after the photon had entered the apparatus. Andrew Manning and colleagues at the Australian National University confirmed it in Nature Physics in 2015 using ultra-cold helium atoms, the first realization with massive particles. The delayed choice experiment is not a thought experiment. It is a measured fact. It has been replicated in multiple laboratories. It is not controversial among physicists. What is controversial is what it means. Wheeler then proposed the cosmic scale version, and this is where it goes from unsettling to genuinely existential. Imagine light from a quasar billions of light years away, gravitationally lensed by an intervening galaxy. The galaxy acts as a natural beam splitter. The photon can take the left path around the galaxy or the right path. If an astronomer on Earth chooses to recombine the two paths using appropriate optics, the photon exhibits interference, wave behavior. If the astronomer chooses to detect which path the photon took, the photon exhibits particle behavior. The astronomer's choice today, right now, in this moment, appears to determine what the photon did billions of years ago, when the light first passed the galaxy. The photon did not have a definite history until someone, billions of years later, decided what question to ask about it. Wheeler was explicit about this. We are participators in bringing into being not only the near and here, but the far away and long ago. Read that sentence again. He is saying that your act of observation, right now, plays a role in determining what happened at the beginning of the universe. Not metaphorically, physically. He drew a diagram he called the self-excited circuit. Picture a large capital U. At one end is the Big Bang. The universe expands, cools, forms stars, produces heavy elements, produces planets, produces life, produces consciousness, produces physicists. At the other end of the U is an I, an observer, and the observer is looking back at the Big Bang. The U curves because Wheeler believed and stated explicitly that the act of observation at one end of cosmic history reaches back and confers reality on everything that came before. The universe does not exist out there, independent of all acts of observation. He wrote, "It is in some strange sense a participatory universe." He put it even more bluntly elsewhere. No phenomenon is a real phenomenon until it is an observed phenomenon, and that we are participators in bringing into being not only the near and here, but the far away and long ago. This is not mysticism. This is not woo. This is John Archibald Wheeler, the man who explained nuclear fission, who named black holes, who trained Richard Feynman, writing in published physics papers and edited academic volumes. And what he is saying is that the universe's past does not exist in a definite state until an observer asks a question about it. Reality is not something you find. It is something you create by the act of looking. He formalized this with a concept he called it from bit. He introduced it at a Santa Fe Institute conference in 1989. Every item of the physical world has at bottom an immaterial source and explanation, he wrote. What we call reality arises in the last analysis from the posing of yes or no questions and the registering of equipment-evoked responses. In short, all things physical are information theoretic in origin, and this is a participatory universe. He then drew the causal loop explicitly. Physics gives rise to observer participancy. Observer participancy gives rise to information, and information gives rise to physics. It is circular, it is self-referential, and Wheeler insisted this was not a flaw in the reasoning, it was the point. Wheeler illustrated the concept with an analogy he called negative 20 questions. A guesser leaves the room, believing the group has agreed on a secret word, but the group has agreed on nothing. Each person answers the guesser's yes or no questions while maintaining consistency with all previous answers. Is it alive? Yes. Is it bigger than a bread box? No. The answers constrain the space of possibilities, and by the end, a specific word has been settled upon. But the word did not exist before the questioning began. It was created by the process of asking, constrained only by internal consistency. Wheeler believed physical reality works exactly the same way. The properties of the universe are not pre-existing facts waiting to be discovered. They are outcomes generated by acts of observation, constrained only by self-consistency. The electron does not have a definite position until someone measures its position. The photon does not have a definite path until someone asks which path it took. And the fundamental constants do not have definite values in some ultimate sense. They are the values that are consistent with a universe that contains beings capable of measuring them. The 20 questions have been asked, and the answers are what they are, not because they were predetermined, but because the asking created them. This idea, which seemed almost incomprehensibly abstract when Wheeler first proposed it, has aged remarkably well. Seth Lloyd at MIT published Programming the Universe in 2006, arguing that the universe literally is a quantum computer that has performed roughly 10 to the 120th operations since the Big Bang. Vlatko Vajdrel at Oxford published Decoding Reality in 2010, making the case that quantum information is more fundamental than matter or energy. The holographic principle, proposed by Gerard 't Hooft and developed by Susskind, says that the information content of a volume of space is encoded on its boundary, measured in Planck area units. The Bekenstein-Hawking entropy formula for black holes, one of the most precisely confirmed results in theoretical physics, is an information theoretic statement. Physics has been moving toward Wheeler's position for decades, even when physicists are reluctant to say so explicitly. I want you to understand the implication of this for the fine-tuning problem, because it changes everything. If Wheeler is right, the fine-tuning of fundamental constants is not a clue about the origin of the universe. It is not evidence of design. It is not a selection effect in a multiverse. It is a tautology, a logical inevitability. The constants are what they are, because anything else would not produce observers, and without observers, the questions are never asked, the information is never registered, and reality never crystallizes into existence. The universe does not tolerate observers. It demands them. They are not a byproduct of physics. They are a precondition for it. This is where Hoyle's insight reaches its full, unsettling depth. In 1953, Hoyle looked at the fact that carbon exists and reasoned backward to predict a nuclear resonance. He deduced a property of the universe from the fact of his own existence. Wheeler's framework says this was not clever reasoning. It was the structure of reality revealing itself. The chain of causation does not run from the Big Bang forward to Hoyle. It runs from Hoyle backward to the Big Bang. Existence works in reverse. Observation is not the end of the causal chain. It is the beginning. When Hoyle wrote about a super-calculating intellect that had monkeyed with physics, he was groping towards something he could sense, but could not name. The vocabulary did not exist yet. He was an atheist. He did not mean God. He did not mean a designer sitting outside the universe adjusting dials. What he meant, I think, was that the numbers looked like they had been chosen deliberately, with intent, and the only entity he could imagine doing the choosing was some form of intelligence. Wheeler provided a different answer decades later. There is no external intelligence. There is no designer. The universe chose its own constants, but it could only choose them through the act of being observed. The intelligence Hoyle sensed is not outside the universe, it is inside it. It is the process of observation itself, looping backward through time, settling the values of constants that had to be what they are for the loop to close. And if that sounds like the universe is a self-constructing, self-observing, self-justifying system that exists because it must, that is exactly what Wheeler proposed. He called it the self-excited circuit. Paul Davies described it as a closed causal loop. Cosmos gives rise to life. Life gives rise to mind. Mind gives rise to cosmos. The snake eats its tail. This connects, almost inevitably, to the simulation argument. Nick Bostrom published his trilemma in 2003. Either civilizations destroy themselves before developing sufficient computing power, or they choose not to run ancestor simulations, or we are almost certainly living in a simulation. If Wheeler is right, that reality is information theoretic at bottom, then the substrate question, whether the computation is happening on silicon or on some deeper physical fabric, becomes secondary. The universe is already a kind of computation, a self-referential one. The simulation argument is not a challenge to Wheeler's framework. It is a special case of it. Now, I should say that I am not personally persuaded by the simulation argument in its strong form. I think Sabine Hossenfelder has raised valid objections about whether you can actually simulate low-level physics while ignoring short-distance details. And there is a philosophical sleight of hand in Bostrom's trilemma that bothers me. The assumption that simulated consciousness is identical to biological consciousness. We do not know that. We do not even know what consciousness is, but the connection between the simulation argument and Wheeler's participatory universe is real, and it points to something that I think is genuinely important. The most serious theoretical frameworks for understanding fundamental physics are converging on the idea that information, not matter, not energy, not space-time, is the deepest layer of reality. And if that is true, then the fine-tuning problem looks very different. It is not a question about why matter arranged itself in an unlikely way. It is a question about why information organized itself into a self-consistent, self-observing structure. And Wheeler's answer to that question is that it had to, because that is what information does. John Barrow pointed out that in a simulated reality, we might expect occasional glitches, small drifts in the supposed constants and laws of nature over time. This was tested. The espresso spectrograph on the Very Large Telescope measured the fine structure constant across 8 billion years of cosmic history and found, in a 2022 paper by Murphy and colleagues, a variation of 1.3 plus or minus 1.3 parts per million, consistent with no variation. The constants are not drifting. Whatever set them is holding them steady. And that brings us, at last, to what the numbers actually mean. I have walked you through 6 things. A nuclear resonance in carbon that should not be where it is. a pattern of fine-tuning that spans all of physics, a cosmological constant prediction that was wrong by 120 orders of magnitude and then corrected by the Anthropic principle, a multiverse that explains the pattern but cannot be tested, a Darwinian alternative that makes predictions but sits on the edge of falsification, and a framework from the most important physicist you have probably never heard of that says the universe does not permit life, but requires it. None of these are fringe claims. Every single one is published, peer-reviewed, and taken seriously by working physicists. The Hoyle state has been measured to 5 significant figures. The cosmological constant discrepancy has been confirmed for nearly 6 decades. Weinberg's prediction was validated by a Nobel Prize-winning observation. Wheeler's delayed choice experiment has been confirmed in laboratories using both photons and massive particles. The multiverse follows logically from 2 of the most studied frameworks in theoretical physics. The pattern is real, the explanations are all incomplete, and the most complete one, the one that actually accounts for the full scope of what has been observed, the one that turns the fine-tuning from a mystery into a structural requirement, is the one that most physicists will not teach in their classrooms because it says something about the nature of reality that the discipline is not equipped to handle. It says physics is not about discovering the universe, it is about completing it. And in 2024, the data got stranger. The DESI experiment, the dark energy spectroscopic instrument, released its first-year results showing hints at 2.5 to 3.9 sigma that dark energy is evolving, that it is getting weaker over cosmic time rather than remaining a strict cosmological constant. The second-year data in 2025 using 14 million galaxy redshifts strengthened this to 2.8 to 4.2 sigma. The independent Dark Energy Survey found a concordant 3.2 sigma preference. If these hints harden to 5 sigma, it would be the most significant cosmological discovery since 1998, and it would add an entirely new dimension to the fine-tuning problem. Because a cosmological constant that changes with time is not just unexplained, it is a sign that the vacuum itself is dynamic, that the ground state of reality is shifting beneath everything built on top of it, and that the fine-tuning is not a fixed condition, but a moving target. And in the background, a quieter result has been tightening the screws. The espresso spectrograph on the Very Large Telescope, the most precise spectrograph ever built for measuring quasar absorption lines, published results in 2022 showing that the fine structure constant has not varied by more than about 1.3 parts per million over the last 8 billion years. Earlier claims of variation, published by John Webb and colleagues using older instruments, appear to have been caused by wavelength calibration errors. The constants are not drifting. Whatever set them is holding them steady across billions of years of cosmic time to a precision that our best instruments can barely resolve. Meanwhile, the theoretical landscape has grown more contentious, not less. Qumran Vafa's swampland program, which argues that stable de Sitter vacua may not actually exist in string theory, threatens to pull the rug out from under the entire 10 to the 500th landscape that supports the multiverse explanation. If the swampland conjectures hold, there may be no vast ensemble of vacuum states for eternal inflation to populate. The anthropic landscape would collapse, but a 2024 paper in Physical Review D showed that a multiverse can be realized even within swampland constraints. So the debate continues. Nobody knows. That is the honest state of the field. The theorists are arguing, the experimentalists are measuring, and the numbers keep coming back fine-tuned. I want to go back to where we started. Carbon, 7.6549 million electron volts. That is the energy of the Hoyle state, the excited nuclear level in carbon-12 that Fred Hoyle predicted from the fact of his own existence, and that Ward Whaling's team confirmed in a basement in Pasadena in 1953 using an accelerator. They moved on tennis balls. That number sits inside a window so narrow that a 0.5% shift in the strong nuclear force would erase carbon from the universe. It exists for no reason that physics can explain from first principles. It cannot be derived from any deeper theory. It is measured, not predicted. And if it were not exactly where it is, you would not be here to know about it. The 1983 Nobel Prize in Physics was awarded to Subramanian Chandrasekhar and William Fowler. Fowler was cited for his theoretical and experimental studies of the nuclear reactions of importance in the formation of the chemical elements in the universe. Hoyle, whose 1946 and 1954 theoretical papers founded the entire field of stellar nucleosynthesis, who made arguably the most successful prediction in the history of nuclear astrophysics, who co-authored the legendary B²FH paper with Margaret Burbidge, Geoffrey Burbidge, and Fowler in 1957, a paper that reviews of modern physics, published at a staggering 104 pages and that remains one of the most cited papers in the history of astrophysics, was not included. Fowler himself acknowledged in his Nobel autobiography that the grand concept of nucleosynthesis in stars was first definitely established by Hoyle in 1946. Geoffrey Burbidge wrote in Science that Hoyle should have been awarded a Nobel Prize. John Maddox, the editor of Nature, called the omission shameful in Hoyle's obituary. The suspected reasons are these. Hoyle had publicly criticized the Nobel Committee's 1974 decision to exclude Jocelyn Bell Burnell from the Pulsar Prize. He had championed increasingly heterodox ideas, including panspermia, the claim that some diseases were seeded from comets, and the assertion that the fossil Archaeopteryx was a forgery. He was, in the words of people who knew him, deliberately provocative and immune to institutional pressure. The Nobel Committee, it appears, decided that Hoyle was too much trouble, that the field owed its existence to his theoretical framework, was apparently insufficient to overcome the inconvenience of his personality. He was knighted in 1972, which is something. He published science fiction novels, including The Black Cloud, which depicted an interstellar intelligence threatening Earth and which is still read today. He never reconciled with the cosmological establishment over the Big Bang, maintaining a modified steady-state position until the end of his life. He suffered a serious hiking accident in November 1997, falling in Shipley Glen near his native Gilstead, the same Yorkshire countryside where he had grown up. He was found 12 hours later by a search dog, lying in the dark at the bottom of a gully. He spent 2 months in hospital and never fully recovered. He died on August 20th, 2001 in Bournemouth at the age of 86. The man who saw the pattern first, who looked at a nuclear energy level and understood what it meant about the nature of reality, who predicted a number from the fact that he existed and was proved right to 5 significant figures, was denied the recognition that his work merited because the scientific establishment found him inconvenient. That should make you angry. Not just on Hoyle's behalf, though there is that, but because his story encapsulates everything that is wrong with how physics handles the fine-tuning problem. The data is there. The pattern is there. The numbers are measured and confirmed. And the field's response has been, for decades, to either ignore the implications, bury them inside untestable multiverse speculation, or treat anyone who takes them seriously as philosophically suspect. This was published, verified, and then quietly filed under things we do not discuss. So, what do the numbers actually mean? I do not know. Neither does anyone else. That is the honest answer, and I think you deserve it. But I can tell you what the frameworks say, and I can tell you which one the math supports, and I can tell you why physicists do not talk about it. The multiverse says the fine-tuning is a selection effect. We observe these values because we could not observe anything else. This is logically coherent and empirically empty. It may be true, it cannot be tested. It is not an explanation in any sense that would have satisfied Galileo, Newton, or Einstein. Cosmological natural selection says the fine-tuning is a Darwinian outcome. Universes evolve toward configurations that maximize reproduction through black holes, and life-friendliness is a correlated side effect. This is creative, testable, and quite possibly wrong. It makes predictions that sit at the margins of current observations. Wheeler's participatory anthropic principle says the fine-tuning is a logical necessity. The constants are what they are because anything else would not produce observers, and observers are not optional. They are not a consequence of physics. They are a condition for physics. The universe is a self-excited circuit. Observation creates reality, and the reality that observation creates is one that, by construction, permits observation. The math supports Wheeler more than most physicists want to admit. The delayed choice experiment is confirmed. The role of the observer in quantum mechanics is experimentally established, whatever interpretation you prefer. The idea that information is more fundamental than matter or energy has gained traction through the work of Seth Lloyd, Vlatko Vedral, and the holographic principle. The concept that the universe is in some deep sense computational or information theoretic is no longer fringe. It is mainstream physics, spoken about carefully and in qualified language, but mainstream. What is not mainstream is the conclusion Wheeler drew from it, that the universe needs you, that you are not an accident, not a byproduct, not a lucky arrangement of atoms that happens to be capable of contemplation, that you are a necessary component of the system, that without observers, the wave function never collapses, the questions are never asked, the information is never registered, and reality remains in a state of unresolved superposition. Not dead, not alive, not anything. Waiting, Hoyle was right, but not in the way he thought. There is no supercalculating intellect. There is no designer sitting outside the universe adjusting constants with a dial. There is something stranger. There is a universe that does not function without something inside it capable of asking why it functions. The fine-tuning is not a clue about who built it. It is a constraint equation, and you are the variable it cannot be solved without. Look at the numbers one more time. The Hoyle state at 7.6549 million electron volts, confirmed to 5 significant figures, sitting inside a tolerance window of 0.5%. The cosmological constant at 10 to the negative 122nd. In Planck units, the most precisely tuned quantity in nature, non-zero at exactly the value Weinberg predicted by assuming the universe requires observers. The strong force coupling at 0.1179, sitting inside a band of a few percent between a universe of pure hydrogen and a universe of pure helium. The cosmic density tuned to 1 part in a million billion at 1 second after the Big Bang. The fine structure constant measured to 81 parts per trillion, occupying a sliver of parameter space that permits both chemistry and stellar burning. 3 spatial dimensions, not 2, not 4, 3. The only integer that permits stable atoms and stable orbits simultaneously. Each of these numbers was measured independently in different laboratories by different teams using different instruments across a span of 7 decades. They have nothing to do with each other physically. The nuclear resonance in carbon has no connection to the vacuum energy of empty space. The strong force has no relationship to the number of dimensions. These are constraints from entirely separate sectors of physics, and they all converge on the same conclusion. The universe is tuned with extraordinary precision for the existence of beings capable of noticing that it is tuned. And nobody can explain why. This was confirmed, published, peer-reviewed, and replicated. And it should have been front-page news for the last 50 years. Instead, physicists acknowledged it in technical journals, invoked the multiverse in popular books, and moved on to topics that feel less philosophically dangerous. The Lewis, Barnes, and Goff Review, published in 2025 by Cambridge University Press, surveyed the entire state of the field and concluded, in their words, that very small changes to the constants of nature make dramatic changes to the resultant universe, and almost all other possible universes would be substantially simpler than ours. That is the current scientific consensus. The universe is fine-tuned. The debate is only about what that means. Fred Hoyle saw it in a nuclear energy level. Weinberg saw it in the cosmological constant. Rees catalogued it across 6 parameters. Wheeler gave it a name and a mechanism. Carter gave it a principle. Ellis warned that the escape hatch was not scientific. Steinhardt warned that the theory was eating itself. Smolin tried to give it a Darwinian explanation and ended up at the margins of falsification. And here you are, made of carbon atoms forged in stellar cores at temperatures above 100 million degrees, held together by a strong force that could not be 2% different in either direction, on a planet orbiting a star that runs on a fusion process tuned to 3 decimal places, in a universe expanding at a rate set by a constant that is either the most precisely tuned number in nature or a signpost pointing towards something we cannot yet see. The calculations have been checked. The Hoyle state is where it is. The cosmological constant is what it is. The fine structure constant has been measured to 81 parts per trillion, and it is not changing. The strong force sits where it sits. These are not theories. These are measurements. And what they measure is a universe that appears to have been arranged with a precision that defies every attempt at natural explanation, for the specific purpose of producing something capable of looking back and asking how it got here. Wheeler would say that the asking is the point, that the universe arranged itself this way because the arrangement is what produces the asking, and the asking is what makes the arrangement real, that the loop closes, that it has to close, that a universe without observers is not a universe at all, just an unresolved wave function, a possibility that never became actual, a question that was never asked and therefore never had an answer. Paul Davies, the physicist and author, summarized Wheeler's framework as a closed causal chain. Cosmos gives rise to life, life gives rise to mind, mind gives rise to cosmos. The snake eats its tail, And if you feel a vertiginous discomfort reading that, if something in your brain resists the circularity, good, you should feel that, because the alternatives are not better. The multiverse asks you to accept an infinite number of unobservable universes on faith. Cosmological natural selection asks you to accept that black holes are cosmic wombs, a theory of everything that derives all constants from first principles, does not exist, and shows no signs of existing. The only option that avoids all of these, the option that says the fine-tuning is just a coincidence, and we should not read anything into it, requires you to believe that the most improbable configuration of physical law that mathematics permits just happened to occur for no reason, and produce the only kind of universe capable of wondering about its own improbability. You can believe that if you want, but you should know what you are believing. And if that is true, if Wheeler was right, then the fine-tuning problem is not a problem. It is a feature, the deepest feature, the one the universe cannot function without. Hoyle, standing in the Kellogg Radiation Laboratory in 1953, looked at the numbers and said something about a super-intellect that monkeyed with physics. He was groping toward a truth he could feel but could not articulate, because the framework that would make sense of what he saw had not been built yet. Wheeler built it decades later. And what it says is not that some intelligence designed the universe for us. It is that the universe is the kind of thing that intelligence makes real. That without the observer, there is no observed. That without the question, there is no answer. That the carbon resonance at 7.6549 million electron volts exists because you are here to measure it, and you are here to measure it because it exists. And the loop has no beginning and no end. And the reason nobody can explain the fine-tuning is that it is not the kind of thing that has an explanation. It is the kind of thing that has a requirement. And the requirement is you. Not because you are special, not because the universe was built for your benefit, not because there is a designer who had you in mind, but because a universe without something inside it capable of collapsing the wave function, registering the information, asking the question, is a universe that never becomes definite. It remains a superposition, a smear of possibilities, a calculation that never resolves. And the fine-tuning, all of it, every decimal place measured to 81 parts per trillion, every nuclear resonance sitting inside a 0.5% window, every cosmological constant tuned to 120 decimal places is what the resolution looks like. It is the signature of a universe that made itself real by producing something that could look at it. That is not a theory. That is what the math says. And the fact that you have never been told this, that this pattern and these numbers and this framework have been sitting in the published literature for decades without ever becoming part of the public conversation about what the universe is, should tell you something about how comfortable the scientific establishment is with the implications of its own discoveries. The data is there. It has been there since 1953. It was confirmed, expanded, replicated, and refined by some of the most accomplished physicists in history. And the story it tells is the one you just heard. The universe is not a place you happen to be in. It is a process that you are part of, and without you, it does not run.